Hello everyone, welcome to the Material Science class, MEC 300. This is the second video of Chapter 3. Chapter 3 we are discussing the structure of crystalline solids. These solid materials or this material type that their microstructure consists of or contains so many crystals. And over the last video we have defined what does it mean crystal, what does it mean crystal structure. For example, the crystal structure is the way how we are arranging atoms inside the material to form a material. The objective of this chapter is first to try to fix some of the important keywords like crystal structure and other things that we are going to cover through the rest of the chapter, and the importance of these keywords and phenomena and things that we are going to cover through chapter 3 that will be used as well through the rest of the course, especially chapter 4, 5, and 7. So that's why it is highly important, and we are taking enough time to cover these and fix these keywords. Why? Because they are important for the next chapters as well. The main other objective of this chapter is to try to understand how the material properties would be related to the way of arranging atoms inside the material. Over chapter 2, we have discussed how the material properties would be related to the forces between atoms, between molecules, whatever it is, bonding force, intermolecular forces. So we have discussed all of these different types of forces and how they would affect or influence the material properties. This is what we have covered in chapter 2. In chapter 3, we are trying to consider another trend, another effect, which is the way of arranging atoms. This means that if we did changes to the way of arranging atoms inside the material, we are definitely changing the material properties. So we are trying to figure out how these arrangements would influence the material properties. This is the main objective of this chapter 3. And again, it is highly important to understand this chapter because we're going to use it for the rest of the course. Over the last video, we have discussed only 3 slides. We have spent enough time to explain what does it mean a crystalline material, what is the difference between a crystalline material and an amorphous material, polycrystalline material, and the important thing, what does it mean a crystal? And what does it mean the crystal structure itself? And then we discussed the unit cell, that it is the basic structural unit or building block from which any crystal structure is going to be composed. And the key idea for choosing this, there are so many factors that would be used for choosing a unit cell, but the key factor is that when we try to repeat this unit cell many times, we are already forming the crystal itself. And also we define the crystal structure. A crystal structure is the representation of the manner or the way in which atoms or ions or molecules of a certain material are arranged. So the arrangement, the way by arranging atoms, this is what does it mean a crystal structure. This is what we have discussed over the last video. In today's video, we're going to focus on the different types of crystal structure that would be used for or are commonly known for metals. So the focus is over metals. Why metals over this part? Because as we mentioned before, all metals and many of the ceramic material and some of the polymers, they are crystalline material. It means that they do have a crystal structure. And since the title of this chapter is the structure of crystalline solids, so the focus is over crystalline material. And definitely, if we could understand the crystal structure of metals, definitely you can have very similar crystal structure for the other material like ceramics and polymers. But as I said, so that's why the focus here is going to be over the most common, and this is the objective of this video, is what are the most common crystal structures for metals, which are 3 crystal structures that we are going to discuss in detail over this video, which are the face center cubic, body center cubic, and the hexagonal close packed crystal structure. So these are 3 different crystal structures. So again, what does it mean a crystal structure? These are 3 different ways of arranging atoms inside the material to form a metal, to form a material. These Fcc, Bcc, and hexagonal HCP, so these are the abbreviation. We can give it like Fcc, which stands for F, face, C, centered, C, cubic. So Fcc, Bcc, which is body, center, cubic, or HCP, which stands for hexagonal close packed crystal structure. These crystal structures are common. Many of metallic materials, they are having this one of these crystal structure. But this doesn't mean that this is the only crystal structure. No, we have different types of crystal structure, so many, but these are the three most common types of crystal structure that commonly known for many of the metal materials. So that's why we are focusing over these three. Another thing that you should understand, that these three crystal structure, they could be found, any one of them are found in ceramic material, are somehow found in polymer. Polymer, it is a special thing. Polymer, it is a special material structure which in many of the cases is different than ceramic material or the metallic material. So again, the focus is going to be over these three crystal structure, the FCC, BCC, and HCP crystal structures. So metallic crystal structure, atoms of a metal crystal, as we mentioned before in chapter 2, are bonded by a metallic bond. And the metallic bond, if you remember this from chapter 2, that we do have two atoms, two metals, they're gonna form a metallic bond, which is very common by having like a cloud of free electron surrounding all of these atoms of the metallic material. And this is the main reason behind the good conductivity for metals and the high ductility for metals, as we discussed in chapter 2. So I highly suggest that you go over these things again of the metallic bonds to understand, or just to memorize and remember these things, how it works. Anyway, we do have three relatively simple. So these are the simple crystal structures that could be found for most and many of the common metal materials, which are the FCC, BCC, and HCP crystal structure. These crystal structures differ in the geometry, in the coordination number, and the atomic backing. So three things that distinguish the FCC crystal structure from the BCC crystal structure from the HCP crystal structure. So again, these crystal structures are three different ways of arranging atoms inside the material to form a material. What makes this crystal structure is different than the other one? Three main things. There could be some other things, but these are the three main factors that distinguish the face center body center cubic from the body center cubic from the hexagonal crossback, which are the geometry, which depends on the shape, how many atoms. So the geometry includes so many things: the shape of the unit cell of this crystal, and the number of atoms that would be located inside this unit cell. This depends on the geometry. Also, they are different in something that we are gonna call as coordination number. This coordination number, simply, it is a material property. It is a property of the crystal. To be more accurate, it is a property of a crystal. It is something that distinguishes one crystal from the other one, which depends on the way of arranging the atom again. So it doesn't depend on the atom type. The atom type would be different, not in the same. Like you may have a crystal or a unit cell that is made of aluminum atoms. You do have another crystal that is made of a copper atom. So the atom type is different. Here we are not talking about material type. We are not talking about the atom type or the element type, but we are talking about the arrangement, how we are arranging these atoms. So the coordination number, it is a property of the crystal structure, which is what exactly this number? It is the number of the nearest neighbor or the touching atoms of an atom. So like if you do have a unit cell, as we discussed before, because I've mentioned this word before, unit cell, this is the smallest button or block or thing or unit. If you choose it and you try to repeat it, you're gonna form the entire crystal back again. So the focus here, as I mentioned, what is the importance of choosing this unit cell? And instead of wasting time to study the entire crystal that include millions of atoms, that is fine if you could figure out or study just one single unit cell. All the properties that you're gonna derive from this unit cell will be representative to the entire crystal, as we discussed over the previous video. So that's why here, instead of, for example, if you do have a crystal that is FCC, and instead of studying all of these atoms together and count how many atoms and so on, it will be difficult for you to do so. But it will be easy if you just consider a unit cell and study this one, and these properties will be the same for the entire crystal. Whatever it is, FCC, BCC, or HCP, or any other crystal structure. Make sense? So that's why the focus here, when we study these geometry, the coordination number, and the atomic backing factor, these three quantities, when we try to study them for these three crystal structures, we're going to consider a unit cell. We're going to assume a unit cell of each one of these crystal structure, and we're going to study the geometry, the coordination number, and the atomic factor. The things that we're going to derive from our study for this unit cell will be represented for any face-centered cubic crystal structure. The same thing for BCC and HCP crystal structures. Make sense? One of these properties or phenomena is the coordination number. This coordination number, it is a property that depends on the crystal structure. It is not independent on the material type or the element type. It depends on the crystal structure, which exactly the number of the nearest atoms or neighbor atoms of an atom that belong to the unit cell. So if you choose an atom within the crystal or even within the unit cell, and you try to count how many other atoms who are in direct contact, who are tangent, touching this atom, if you count them, this number gives you the coordination number. So again, simply, the coordination number, if you choose any atom within the unit cell, or within the entire crystal, the big crystal, or just the unit cell, the same, you're going to end up with the same number. So if you choose an atom, and you try to count how many other atoms who already tangent or touching this atom, this is going to give you the coordination number. This coordination number will be different depending on how we are arranging atoms inside the crystal. It will be different depending on the crystal structure. So that's why we are saying there is a property for the crystal structure. So we're going to know how we can calculate the coordination number for FCC crystal structure, for BCC and HCP crystal structure, for these three. Also, we're going to study the geometry. What is the shape? For example, from the name cubic, it means that the geometry, the shape of this unit cell or the unit cell of this crystal structure is going to be cubic. The same thing for the BCC, but this one is going to be hexagonal. It comes from the name itself. So they will be different in the geometry. They will be different in the number of atoms that would be located inside one single unit cell that is representative to this crystal structure. Also, another factor that will be different from one crystal structure to the other is the atomic backing factor, which we're going to give it the symbol APF, stands for atomic backing factor, which is the sum of the volumes of all atoms. So you're just going to count how many atoms. So this count, it is one of the properties of this crystal structure that should be counted or calculated. We're going to know how many atoms that would be located inside one unit cell of each one of these crystal structures. So if you're going to count the atoms and you're going to calculate the volumes of all of these atoms that form a unit cell of these crystal structures, and you divided by the overall unit cell volume, this is going to give us the atomic backing factor. If the volume of the atoms located inside the unit cell divided by the entire volume is a big number, this indicates that this unit cell, it is dense. Dense, it means that it contains so many atoms. It is crowded with atoms, filled with atoms. But if the atomic backing number is lower, is decreasing, it means that the density of the atoms inside the unit cell is decreasing. It means that the number of the atoms in general, not exactly the number, it means that it is not crowded with atoms as the one with the higher atomic backing factor. So as we increasing, so this atomic backing factor gives us indication how it is crowded with atom, the unit cell or the crystal, how much of crowdedness of this atoms inside the unit cell, whatever it is, crowded or not crowded with atoms, it depends on, it gives indication somehow on the density of the atoms inside the material, and which definitely will be related to the entire density of the material. Any material, and this is what we studied before in physics, one of the physical properties of material are the density, is the density. So the density of the material, the mass density, it is related on this atomic backing structure or this atomic backing factor somehow. There is a relation between them. This atomic backing factor, it gives indication how dense is the unit cell or how much of crowdedness of these atoms inside that filling the unit cell is in comparison to any other atomic crystal structure. This is the atomic backing factor. So these three crystal structures, they are different in these three quantities. And now the objective through this first part of this video is just to understand how we're gonna calculate. I'm gonna show you how we can calculate this geometry, coordination number, and atomic backing factor for these three crystal structures. Make sense? So let us start with the Fcc crystal structure, which is face center cubic crystal. Here we're gonna study the unit cell, which is representative to the entire Fcc crystal structure. So the unit cell of a Fcc crystal structure is a cubic. So this is one different thing in terms of geometry, that it is cubic shape. It's just cube. And we knew from physics, from mathematics, from other so many things, that any cubic shape, all the edges of the cube, they should be equal, right? So we're gonna consider here A. This A, it is like a lattice constant. It's known as lattice constant. This is also like a crystal property or a material property. For example, if you Google the lattice constant for aluminum, it's gonna give you a certain value. The lattice constant for copper is gonna give you another value. So it is a material property that also depends on the material type and the crystal type. Okay, so this A will be different from one material to the other material. Why? Because it depends on the size of the atom. So this R stands for the radius of the atom. So this is the atomic radius. But the A, it is the unit cell length or the lattice constant. So this is the A. All of these are material properties. For example, the radius, which refers to the size of the atom of the aluminum, will be different than copper than any other material. So R and A, these are two material properties that depend on the material type. You can Google them, and there is a table that I'm gonna provide for you for this A and R and how you're gonna find them. Okay, so they are different from one material type to the other material type. So let us consider that we do have this atom. This R stands for the radius of a spherical atom. Here we are represented, as we discussed over the last meeting, that if we consider even the hard sphere model or the reduced field model, we are representing the atom as a sphere. And sphere, it requires only one geometrical dimension or geometrical property, which is the radius. The radius or the diameter of the sphere is a representative of any spherical shape, right? So here we are assuming atoms as spheres, and each one of this sphere will have an R, and this R will be a representative for all the atoms that form this Fcc crystal structure or any other crystal structure. Make sense? So R stands for the radius of the atom, and A stands for the size or the edge or the length of the edge of the cubic crystal. The length of this edge is going to be A, the length of that edge will be A, and so on. All the edges will be equal to A, which is known as the lattice constant or the unit cell length, which could be related to R through this relation, where A equals to 2R times the square root of 2. This relation is fixed for any Fcc crystal structure. Here we are talking about the geometry, the shape of this unit cell, for a crystal that is Fcc crystal. So the unit cell of Fcc crystal, it is cubic geometry. This is one thing. It has a cubic shape with atoms located at each of the corners and centers of all cubic face. This is another important thing. Here we're still talking about the geometry, the shape of this unit cell. What distinguishes, for example, Fcc crystal from the Bcc crystal that we are going to discuss next is the way of arranging. First thing, that the crystal, it is cubic. This is one difference or one property. Another thing, that there are atoms who are located at the corners of this cubic shape. Like you're gonna have one atom here, and there should be one atom here, an atom here, atom. So at each corner there should be an atom. Whatever it is, a complete atom or a part of an atom, this thing that we are going to discuss next. But anyway, assume that at every corner there should be an atom, which are these blue atoms as represented in this reduced spherical model. Plus, in addition to this, there are some other atoms who are located at the center of each face. How many faces for any cubic shape? We do have 6 faces in total. So at every center of these 6 faces, there should be an atom located there. Located exactly at the center, like this yellow atom, and there is another atom. There should be another atom on the back, this atom on the left, one on the top, one on the bottom. So this is how we are arranging atoms inside a unit cell that has a cubic shape based on the Fcc crystal structure. I'm just gonna skip some slides here, and then I will explain these slides definitely, but let us move here to the BCC just to know and understand the difference between Fcc and Bcc crystal structure. In the Bcc crystal structure, the unit cell of a Bcc crystal structure has a cubic geometry. So there is nothing different. It is still cubic. But the difference is how we are arranging atoms. For example, atoms are located at each corner. There is no difference here. In the Fcc, we do have atoms at each corner. But we do have one single atom that located at the cube center. We do have a cube, and there is a center for that cube. So there should be one atom in the core, inside the cube itself, and there are some other atoms who are located at the boundaries, at the corners of this unit cell. As is shown here, we do have only one atom in the core. In the middle, like you'd have a box and you just hanging a sphere inside at the core of this box, in the middle of this box, and you'd have some other atoms who are located at the corner. This is the body center. So that's why body center, it means that there is an atom that is located at the center of that body, at the center of this box, at the center of this cube. So that's why we got the name as body center cubic, because there is cubic geometry and there are some other atoms who are located at the corners. If you compare this shape or this arrangement, so the difference here is how we are arranging atoms. But there in the Fcc crystal structure, we do have at every corner there is one atom, but the difference is that we do have at the center of every face there is an atom. That's why we got the name face center, not body center. Face center, it means that over the face of every unit cell, there should be an atom that located at the center of that face. So that's why we got the name as face center. But there, we do have one atom that located in the core, and there is no atoms over the faces. This is the difference between the Fcc crystal structure and Bcc crystal structure in terms of geometry. Make sense? So here we are discussing geometry. Both are cubic, but the Fcc, it has atoms at the corners and atoms located at the centers of their faces. Make sense? We do have in total 6 faces, and we do have at these their centers, there should be some atoms. So this is the geometry of the Fcc crystal structure. And as we mentioned, we do have this A, which is unit cell length. It is a material property that depends on the material type, and it could be related to R, which is the radius of the atom, using this relation. How we can figure out or drive this relation? This relation can be simply driven from the geometry of this triangular shape. If you choose this hypotenuse or this diagonal here of this face, just choose one face for the Fcc crystal structure. And this is the hypotenuse, and this is one edge A, and there is another edge. So this is going to give us like a triangular shape. This triangle, if I ask you to calculate the hypotenuse of this triangle, this edge, it should equal to the square root of A square plus A square, right? This is from the trigonometry, from mathematics. So this is going to give us at the end A square root of 2. Agree? So this is one edge, this is the hypotenuse. So this is square of this edge plus the square of this edge under the square root. This is going to give us A square root of 2. And if I ask you to calculate the length of this edge or this hypotenuse in terms of R, which is the radius of the atom, we do have here 1 R over this edge. This should be 1 R, which this distance from that point to this point, 1 R. And this should be the over diameter, the entire diameter of one atom, which should be 2R. So we do have here 1R, and in the middle from that point, this point, we do have 2R, and from here to there, we do have another R. So if you sum, this is gonna give in total 4 Rs. 1r, second, and 2r. So this should equal to 4r. If you divide by square root of 2, you're going to end up with this relation. So this is going to give us a equals 4r divided by square root of 2, which is going to give us 2 square root of 2r. This is going to give us the a, which is the lattice constant in terms of the atomic radius. It means that if you know for some reason, or you already given r, which is the atomic radius for this unit cell, you can simply calculate the edge, how much it is. Make sense? And usually something that you should understand that this atomic radius, it comes in nanoscale. Nanoscale is nanometer. Nanometer, it is 1 nanometer. 1 nanometer, it is equivalent to 10 to the negative 9 meter. So it is very tiny thing, very small thing. It means that this A, it is very small dimension. It comes in nanometer in many of the, for many of the materials. Make sense? So this is from the geometry. And now let us move to the number. Also something that is related to the geometry is the number of atoms. And it is important to know how you can calculate this number of atoms that belong to a unit cell that is representative to the FCC entire crystal. Here we are studying the unit cell. This is not the crystal. This is just one single unit cell. When it is repeated, it's going to give us the entire FCC crystal structure. Make sense? So, the unit cell of Fcc crystal structure contains 4 atoms. So, how many number of atoms that form an Fcc crystal? It is 4. For the Bcc, it will be different number. For the hexagonal closed back, it would be different numbers. Okay? And remember that these are not the only 3 crystal structures. We do have so many types of crystal structures. But these are the 3 common types. Okay? So that's why we are focusing on these 3 types. But the thing that we are doing here, you can repeat them for any other crystal structure. So you're going to end up with the same geometrical properties with another geometrical properties, another coordination number, atomic backing factor. So for the Fcc crystal structure, it contains 4 atoms. Its coordination number is 12. Again, what is the coordination number? This is if you choose one atom and you start to count all the neighbors to these atoms, it should be 12. For any Fcc crystal structure, for any material with Fcc crystal structure, its coordination number is 12. For any material with Fcc crystal structure, its unit cell contains 4 atoms, and so on. Its atomic backing factor is 0.74. So how we calculated this number? So we do have here 3 numbers for the Fcc crystal structure. We do have 4 atoms, we do have 12 coordination number, and the atomic backing factor. Why it is 4 atoms? Let us count how many atoms here. Any atom, we said that for the Fcc unit cell, there should be 1 atom at the corner. This atom at the corner, it is shared by 8 unit cells, not just 1. It means that the one single unit cell, it won't gonna take an entire complete atom. Instead, it's gonna take 1/8 of this atom. Why? Because this atom, it is common. It is shared among or between 8 unit cells. Because at every corner, since we have a cubic shape, at every corner, we may have 8 unit cells who could meet together at one corner. It means that this atom, it is shared between 8 unit cells. So every single unit cell is going to take 1/8 of that atom. So each corner atom is shared among or between 8 unit cells. So what does it mean this? It means that this one atom will be divided by 8. So whereas a face center, so this is one thing. So 1 atom at every corner. But how about the face centered atom? This atom is shared between 2 unit cells, not 8. Because there is the face. So one face, it can be shared by only 2 unit cells. 1 unit cell on the right, 1 unit cell on the left, and that's it. It means that this atom that located at the center of that face will be shared between 2 unit cells. It means that every unit cell is going to take half of it. So whereas the face-centered atom belongs or shared between 2 unit cells. So the face-centered 1 unit cell will contain half of an atom at its center face, and it will have 1/8 at every corner. So this is a typical shape and exact shape of the portions of the atoms how are distributing in one unit cell. This is just one unit cell. At every corner we do have 1/8. At every center of the face we do have half of an atom, which are these yellow things. Make sense? So therefore 1/8 of each of the 8 corner atoms. How many atoms, how many corners do we have for any cubic shape? We should have 4 corners on the top, 4 corners at the bottom. So this is 1 corner, this is the second, the third, the 4 on the top, and we do have another 4. And there should be 1 on the back, which is not seen. So in total, we do have 8 corners times there should be 1/8 of an atom at every corner. So this is gonna give us 1 atom. This is at the corners. This is at the corners, right? But how about the face centered? Face center. At the face center, we do have half of an atom, but how many faces do we have for any cubic shape? We do have 6 faces. We do have 1 face, 1 on the front, 1 on the back, 1 on the right, 1 on the left, 1 on the top, 1 on the bottom, 6 faces. So if you multiply 1/2 of an atom times 6 faces, this is gonna give us 3 atoms. So entirely, in total, 1 single unit cell will contain 4 atoms. 1 atom, which is the sum of all the corners, and 3 atoms, which are the sum of all the faces. This is going to give us in total 4 atoms who are forming the unit cell of Fcc crystal structure. So if you have been asked why the Fcc crystal contains 4, because each corner atom is shared between 8 unit cell, and every face center atom, it belongs or shared between 2 unit cells. Therefore, 1/8 of each corner multiplied times the 8 corner atom gives 1 atom, and 1/2 of each of the 6 faces, we have 6 faces, faces gives us 3 atoms. So in total, we're gonna end up with 4 atoms who are forming the entire complete atoms who are forming the unit cell of Fcc crystal structure. Make sense? Now let us move why the coordination number is 12 and how the atomic backing factor is 0.75. We need to prove these 2 numbers. Remember that these are properties of the crystal structure. They are not just dependent on the material type. For any material with Fcc crystal structure, it will have 4, 12, and 0.74. So let us calculate or count the 12 coordination number. We said that this coordination number, it represents, if you choose any atom and start to count all the neighbors to that atoms, you're gonna end up with 12. And in order to do it, you should, for Fcc crystal structure, you should imagine that you do have 2 unit cells. Assume that you do have 2 unit cells side by side. That there is a face that is common between them, like as shown here in this figure. Assume that this is 1 Fcc unit cell, and there should be another Fcc unit cell which is next to it directly. There should be 1 face, which is this face, that is common between these 2 side-by-side Fcc unit cells. If you choose the center atom of that face, this is the atom that you're gonna count its 12 other neighbor atoms. So why there are 12? Let us count. Over the same face, we do have 1 atom, second, third, 4. So now we have 4 atoms over the corners of the same face. So you have 2 unit cells side by side. So there is a common face between them, and choose the center of this face. This is the atom. This atom will not be counted. It is not included in the 12. No, you're just gonna count the other atoms who are closest atoms, the nearest atoms to this atom in the center. We do have 1 atom at this corner, 1 atom at this corner, 1 atom at this corner, 1 atom at the other corner. So these are 4. In addition, over the face, it will not be clear here. So I'm going to represent over the next slide I'm going to show with more detail. But in addition, we do have some other 4 atoms who are located at the centers of the top and the bottom faces of the 2 unit cell. We do have top face, top surface, so these 2 surfaces, two bottom surfaces, and there should be atoms at their centers, right? So this gives 1, 2, 3, 4 atoms. So there is another group of 4 of atoms who are neighbors to this center unit cell. In addition, we do have 2 front faces, 1 face, 2 back faces, because we do have 2 unit cells, and there are, at their centers, there should be atoms. So this gives another 4 atoms. 1 at this center, 1 at this center, 1 at the centers of the 2 back faces of the 2 unit cells. So this gives another 4. So 4 times 3, because we do have 3 groups of 4, this gives in total 12. So how we are counting this? So a face atom belongs to 2 neighbor unit cells. You should consider two neighbor unit cells, 2 unit cells next to each other. This face atom is surrounded by 4 corner nearest neighbor atoms of 4 face atoms of one of the 2 unit cells of one of the 2 unit cells, and 4 other face centered of the other unit cell. This gives like 4 by 4. And it is not 4 by 4, it is 4 3 times. Kind of, you're gonna end up with the 12 number. So it's gonna be much more clear over this representation, how we are calculating this thing. This is the atom that I'm talking about. You do have 2 unit cells, this is 1 unit cell, this is the second one. And there is a face common between them. You're just gonna choose this atom to count its neighbors. Definitely, over all of these unit cells, there should be atoms here at the corners, right? Because in the Fcc crystal structure, there should be an atom at every corner. So there should be this atom which is going to be common between these 2 unit cells, and there is another atom, another atom, another atom. Here we are dealing and assuming that we do have a complete atom. Assume that, okay? So this is going to give us 1 atom, second, third, 4 atoms. So here for this case we have 4 atoms. Very simple, right? Now let us move to the same unit cell, but we're going to consider other group of 4 atoms. The same atom that we are already counting its neighbor. For this unit cell, there should be an atom over this center of the top face, right? And there should be another atom at the center of the top face of the other unit cell. How about the bottom faces? This is the bottom face. Which this one, this is the bottom face, and there should be another bottom face here, right? So over this bottom face, there should be an atom at its center, and over its center, there should be another atom. So these 4 atoms form the other 4 group. So they're gonna be located over like one plane, another plane, not surface. These 4 as like 4 other atoms. So this is atom 1, atom 2, atom 3, atom 4. These atoms are located at the centers of the top and bottom faces. We have 2 on the top for the 2 unit cells, 2 at the bottom for the other for the 2 unit cells. So this gives another 4. And the same atom that we're already counting its neighbor. Now we're gonna consider the centers of the front and back. So we got the top and the bottom. Now we're gonna consider the front and the back of these 2 unit cells. What is the front of this unit cell? This is the front face. And this is the front face of the second unit cell. The back is going to be on the back, which are these two edges are dashed lines. So there should be a center atom here. 1 atom in the center of this face, 1 atom of the center of that face. And on the back also there should be other 2 atoms who are located at the centers of the faces on the back. So this gives another 4. A third group of 4 atoms. This is going to be atom 1, atom 2, atom 3, atom 4. So this gives another 4. If you sum 4 plus 4 plus 4, this gives in total 12 atoms, which gives us the coordination number. This is why we are saying the coordination number for Fcc cubic crystal is 12. Make sense? This is how we can calculate the coordination number for any crystal structure. Your objective is just to choose an atom, whatever in the same unit cell, or 2 neighbor unit cell, or 3 neighbor unit cell. It depends on the crystal structure itself. For Fcc crystal structure to be able to calculate the coordination number, you have to assume 2 unit cells side by side, and then you're going to choose the atom over the face that is common between them. Then you're going to count all the neighbors. If you're going to count them, you're going to end up with 12, which represent the coordination number. Make sense? Now let us move to another phenomena or property of Fcc crystal structure, which are the atomic backing factor. how we can calculate it. This atomic backing factor, again, it represents how dense is this unit cell filled with atoms. The density gives like indication about the density of atoms inside the unit cell. For the Fcc crystal structure, it is with this value, 0.74. It is common for any material with Fcc crystal structure. It's going to be this value. We need to prove it. Okay, so to prove this thing, let us consider the equation of the atomic backing factor. We mentioned that it should equal to the volume of all atoms inside the unit cell divided by the total volume of the unit cell. For the Fcc crystal structure, the volume, it is a cubic. The unit cell, it has a cubic shape. So what is the volume of this cube? The volume of this cube is going to be the cube of its side, of the length of its side. Like this is the side edge of A. So A cube simply is going to be the volume of this cubic shape. Any cubic shape with a side edge equals A. So A cube, this is going to give us the volume of this cubic shape. So the volume of the unit cell, which the denominator here for the Fcc crystal structure is going to be A cube. Very simple. But how about the volume of the atoms that form the unit cell? Here we are assuming that the atom is a spherical, because in reality it is almost a perfect crystal, a perfect sphere. So we are assuming that every atom, it is a sphere. So what is the volume of the sphere? The volume of the sphere is 4 over 3 pi r cube, where r stands for the radius of the atom. And we said that this radius of the atom, it is a material property that is different from one material to the other. They are known. If you time the atomic radius for aluminum, copper, Fe, any metal material, you're gonna find it over Google. And there are lots of textbooks, and I'm gonna provide you a table with these radius values. Make sense? Anyway, so the volume of one atom, it is pi over 4 by r cube. But in the Fcc crystal structure, we mentioned that we do have 4 atoms. So the entire number that should be added in the numerator of this relation, it should be the volume of these 4 atoms. So you're going to multiply 4 times the volume of one atom, which is a spherical. Then you're going to calculate this volume. If you divide by the volume of the entire unit cell, assuming that it is just a cubic shape, forget about the atom that located there, you're going to end up with the atomic backing factor with that number. Okay, so let us do these calculations for the Fcc crystal structure. So the first step to do so, actually, the first step, your objective is just to calculate. Just if you try to stick to these steps. Step 1 is just calculate A, which is the lattice constant in terms of the atomic radius r. And we have done this calculation before over this slide. We got it by 2 square root of 2r. But let us repeat it again here. So, since we are talking about Fcc crystal structure, it means that there should be an atom located at the center of every face. So let us choose the first face here. One face of the Fcc crystal structure. There should be an atom at this center, and there should be another atom at the corner, and there should be another atom at the other corner. And you should understand that all of these 3 atoms, they should be of the same size. But I'm not, since I'm using freehand sketching, my drawing is not accurate. But you should understand that all of them, they do have the same radius. So if you choose this diagonal, this hypotenuse of this triangular shape, this side, it should equal to A, and this side also should equal to A. So from the trigonometry of this triangular shape, this hypotenuse, it should equal to square root of 2a square root of 2, right? Which a squared plus a squared under the square root, this gives us a square root of 2. And the meanwhile, in terms of the radius, this distance, it should be r. This diameter, this is the entire diameter, so it is 2r, not just 1r. So it is 2r, and we do have another r here. So this hypotenuse in terms of the radius, it is equal to 4r. So the 4r, which is the hypotenuse, equals a square root of 2 in terms of the a, which is the side edge, or the lattice constant. So from here, we're going to end up that a is going to be the, if you divide by square root of 2, this gives us 2 square root of 2r. So this is the first step. It's just to do this calculation for the a in terms of r. Then the second step is just to calculate the volume of atoms inside the FCC, since we are talking about the FCC unit cell. One unit cell, assume one unit cell, and your objective is just to calculate the volume. So we agreed before that four atoms form one unit cell of FCC crystal structure, right? And the volume of one atom, it is pi over 3 pi r cubed. So the volume of all the atoms, so this S stands for the atoms as sum, or you can use A stands for atom. No matter what, I'm just trying to stick what is written in the textbook. He's using here VS. So VS stands for the volume for the four atoms, or the atom that form this unit cell. So they are in total 4 times the volume of one sphere, because every atom will be sphere. So this is going to give us 4 divided by 3 by r cubed. This is the volume of the sphere. If you did the calculation, this is going to give us 16 divided by 3 by r cubed. Remember that I'm doing the calculation in terms of, in symbolic form, in terms of r, in terms of the atomic radius. Then the third step, your objective is just to calculate the volume of the cube. So the third step, calculate the volume of the unit cell. Here I'm not talking about the atom. I don't care about the how many atoms or the distribution of atoms inside this unit cell, but I'm just discussing the volume, or calculate the volume of the unit cell itself. The unit cell is cubic. So for any cubic, since we are talking about the FCC crystal structure, its volume of the unit cell, it should equal to a cube. Why? Because its side edge is A, so A cube is gonna give us the volume. But you need to represent this A in terms of R. You're gonna substitute with this relation into the A cube. So this is gonna give us 2 square root of 2R cubed. This in total is gonna give us 16 square root of 2R cubed. So we got the volume in terms of R of the unit cell. We got the volume of all the 4 spheres that form the FCC crystal cell in terms of R, the atomic radius, and we got A in terms of R, everything in terms of R, the atomic radius. Then your objective is just to plug these calculations into this formula. That now you're just gonna calculate the atomic backing factor, which is equal to the volume of all the atoms divided by the volume of the unit cell. So if we did the calculations here, the volume of the sphere of all the spherical atoms, we got it by 16 over 3 by r cubed. So it is 16 over 3 by r cubed divided by this volume of the unit cell, which we got at 16 square root of 2 r cubed. So simply the r cubed will be cancelled with the r cubed. The 16 will be cancelled with the 16, and this 3 will be moved to the denominator. So this is going to give us at the end pi over 3 square root of 2. So this is the exact value. This is the exact value of the atomic backing factor for FCC crystal structure. Remember this number, it is pi divided by 3 square root of 2. If we use the calculation, this is going to give us over the calculator 0.7408048 and some other digits. So if we round this number, considering only 2 decimal numbers, so we're going to end up with the 0.74, which is commonly known for all FCC crystal structure, that their atomic backing factor is 0.74. It means that it is one unit cell, it is not 100% filled with atoms. No, it is only 75% of the unit cell is filled with atoms, and the rest is just void, spacing between these atoms. Make sense? This is what does it mean, the atomic backing factor for the FCC crystal structure. So this is all for the FCC crystal structure. We mentioned that they do have, in terms of geometry, they are cubic. Their atomic edge, which is A, in terms of its atomic radius, it is 2 square root of 2r. And they contain atoms at every corner, and 1 atom at every center of the 6 faces of the unit cell. And in addition, every unit cell contains 4 atoms. So 4 things to mention about the geometries. All of these are geometries. In addition, they do have coordination number. This is another factor, another property. Their coordination number is 12. Why it is 12? as we mentioned, if we choose one atom at the center, of one phase that is common between two unit cells, and we start to count the atoms surrounding as neighbors to this atom, you're gonna find them 12. Then the atomic backing factor is 0.74, which we just proved, and we did the calculations to prove that it is with this value for the Fcc crystal structure. Very simple. Make sense? So this is for the Fcc crystal structure. Now let us move to the Bcc crystal structure, or the body center cubic crystal. Alright, so for the Bcc crystal structure, as we mentioned before, here it's gonna be much more easy because we understand how it works. So we're just gonna focus on the differences. In the Bcc crystal structure, the unit cell has a cubic geometry like Fcc, and also atoms are located at every corner, and definitely this corner will be shared between 8 atoms, exactly like the Fcc crystal structure, nothing new. But the new thing is that there is no atoms at the centers of the faces, but instead we do have one big atom, not big, the same atom, one whole atom, complete atom that located at the core of this box or this cube, as we mentioned before. This is what distinguishes the Bcc crystal structure from the Fcc crystal structure. And this is gonna make the other quantities like A in terms of R, the unit cell length or the lattice constant in terms of R will be different. The same thing for the atomic backing factor, the number, the coordination number will be different as well. So for example, YA in terms of R is gonna be 4R square root of 3, because simply if you choose the diagonal, I'm just gonna show you how we can drive this relation. So let us consider this cubic shape of the Bcc crystal structure. Remember that there is no atoms located at the faces. So in the Fcc, when we did the calculation for the A in terms of R, this relation, we chose one face of the unit cell. And then we located the hypotenuse and we defined a triangular shape. Then we end up with this relation for the Fcc crystal structure. But for the Bcc crystal structure, here we will not choose a face. Why? Because there is no atoms located at the center of these faces, but instead we do have one atom in the core. So we have to choose the main diagonal of this unit cell. This main diagonal we do have for any cubic shape, it has two diagonals, like your room that you're sitting in. It has a cubic shape. If you choose one corner and you draw a line, visual line to the other corner at the back, at the other end, next to it, this is going to be the main diagonal of this cubic shape. So we do have in total 4 lines, actually 4 corners. You can draw one line here, and there should be one line there, and from here there should be one line, and from there should be one line. But anyway, choose any one of these lines. Like for example, I'm just going to connect this corner of my room to this corner, or this cubic shape, this corner to this corner with, I'm just going to draw a line. This is going to give us a diagonal. And there should be for this bottom face, let us choose this bottom face, which this edge and this edge and this edge. And if you connect this atom to this atom, this will give us the hypotenuse of this bottom surface, right? And then you're gonna have this edge. Your objective is just to form a triangular shape. One of the edges of this triangle, it should be the main diagonal of the cubic shape, and the hypotenuse of one of the faces, like the bottom face, for example, as I'm doing here. So if this side edge, if this edge is A, and this edge definitely is going to be A, and this height, it should be A, because it is a cubic with a side edge of A, which represents the lattice constant or the unit cell constant. It is a material property. It means that this vertical edge will have a length of A. And how about this hypotenuse? This one, this base here will be a triangular shape. This base, this part will be a triangular shape. So you have A and A. It is 90-degree triangular shape. So AA, this hypotenuse will be the A square plus A square under the square root. This is going to give us this edge will be A square root of 2. Why? Because if you choose this small triangular thing, will be seen an upright angle triangle with AA, and this edge will be A square root of 2. This edge, this is what I'm talking about. This is what I draw here. So we still need to work over this big triangle, right? You do have one edge with a length of a square root of 2 and the other edge with a height a. So what should be the hypotenuse of this triangular shape? So this hypotenuse, definitely this one will be this a square plus this edge square, which is going to be the 2a square, because the square of this square root is going to give us 2 and a is going to be a square under the square root. So simply we're going to end up that this entire edge in terms of a, in terms of the side edge of this cubic shape, will be a square root or under the square root of a square plus 2a square. Can we find the same length but in terms of r as we did with the FCC? We choose one face in the FCC, then we calculated the hypotenuse in terms of a, then we calculate the same hypotenuse length but in terms of r. We're gonna do the same for this diagonal. Remember that in your room, in this cubic room, we do have one atom at the corner and we do have one atom over the other corner, and there should be another complete atom in the middle. And all of these three atoms are tangent to each other, touching each other. It means that over this hypotenuse, there should be like a piece of an atom over this corner, and there should be another piece of an atom over the second corner, and there should be one complete atom in the middle. So if I ask you what should be the length of this edge, or this hypotenuse, or this diagonal, but in terms of r, the distance from that point, this point to this point, this distance, it is r. One radius, because we do have one atom. And from this point to this point is going to be 2r, typically as we did for the Fcc crystal structure. And the distance from this point to this point is going to be r. So in total, this edge is going to be 4r. This means that this edge in terms of the radius, it is 4r. In terms of a, which is the lattice constant, it is square root of a squared plus 2a squared. So if we just did the simplification for this relation, we do have 4r equals square root of a squared plus 2a squared. If we consider a as a common factor, it will be moved outside the square root with just a, right? It is a common factor, then you're going to move it out. So this is going to give us 1 plus 2, which will be square root of 3. Then if you divide by square root of 3, both sides, this is going to give us that a equals 4 divided by r square root of 3, because this one will be cancelled with this one, which going to give us this relation. So this is why the lattice constant in terms of the atomic radius for the Bcc crystal structure is different than the Fcc crystal structure, and you have to memorize and remember these relations. For the Fcc crystal structure, it was 2 square root of 2r, but for the Bcc crystal structure, it is 4r square root of 3. Make sense? So this is a different thing. But also another different thing between Bcc crystal structure, this should be BCC, not FCC. Bcc crystal structure and the Fcc crystal structure is that this number, it should be 2 here, but there it was 4. In FCC, one unit cell contains 4 atoms in the FCC, but in the Bcc crystal structure, it is just 2 atoms. How? There in the FCC, we were having one atom at every corner, and this atom was shared between 8 unit cell. It means that every unit cell will take 1/8 of that atom. In addition, we had in the FCC one atom that located at the center of every face, and this atom was shared between 2 unit cell. It means that every unit cell is going to take half. This give us the 4, but here we have only 2. How? We do have atoms at the corners of the Bcc crystal structure. This atom will be shared between 8 unit cell. Typically, like the Fcc crystal structure, it means that every unit cell is going to take 1/8 of this atom. And in total, we do have 8 corners. As we agreed, we do have 4 corners. 4 on the top, 1, 2, 3, 4. And there should be another 4 at the bottom, right? 1 in the back. So if you multiply 1/8 of this atom that located at the corner that is shared between 8 unit cell times 8 corner, this is going to give us only 1 atom. In addition, we do have only another single atom, complete atom that located at the core of this unit cell. This gives us in total 2 atoms. There is no other atoms located over the faces for the Bcc crystal structure. So the unit cell of Bcc crystal structure contains 2 atoms. Why? Because the unit cell contains a single whole atom at its center. So this is 1 atom. And each corner atom is shared between 8 unit cells. Therefore, 1/8 of each of the 8 corner atoms, and the whole center atom gives in total 2 atoms, because 1/8 times 8 gives 1, plus 1 in the center gives in total 2 atoms. The coordination number of Bcc crystal, it is 8. In Fcc it was 12. What is the coordination number again? It is the count of the neighbor atoms to any atom that form this unit cell or crystal structure. It would be easy for us to calculate the coordination number for Bcc crystal structure. It is kind of more complicated for Fcc. In Fcc, we had to assume 2 unit cells, and we chose the atom that located at the common face between these two, at the center of the common face between these 2 unit cells. Then we counted, we end up with 12. Here, it is enough to assume only one unit cell. There is no need to 2 unit cells for the Bcc crystal structure. Then if you choose the core atom, this is the core atom. What are the neighbors to this core atoms? You're gonna end up with 8 atoms, 4 on the top, 4 on the bottom, that located at the corners, the 8 corners of this cubic crystal. So we have 1 atom at this corner, 1 atom here, 3, 4 on the top, and another 4 in the bottom. So this is gonna give us 5, 6, 7, and 8 atoms in total as neighbors who are in direct contact and tangent and touching this core atom, which is gonna give us the coordination number as 8. Very simple, right? How about the atomic backing factor? The atomic backing factor, it is 0.68 for Bcc crystal structure, but for the Fcc crystal structure, it is 0.74. So what does it mean this? This means that the Fcc crystal structure, it is more dense. It is more crowded than the Bcc crystal structure in terms of atoms. 74% of the Fcc crystal structure is filled with atoms, but 68% only of the Bcc crystal structure is filled with atoms. It means that the Fcc, it is more crowded, it is more filled with atoms than the Bcc crystal structure. That's why the atomic backing factor in Fcc is bigger than the atomic backing factor of the Bcc crystal structure. In Bcc crystal structure, it is 0.68. How we can calculate it? Okay, so we're gonna go over the calculation of the atomic backing factor very quick, which is gonna be the same, typically the same procedure that we applied over the Fcc crystal structure. So the first step, if you recall that, we mentioned that your first step is just to calculate the A, which is the atomic lattice, in terms of R. And we just did these calculations there. We did these calculations and we end up with this region. So I'm just gonna repeat it very quick. We said that you're just gonna assume that you do have a cubic shape of this cubic Bcc crystal structure, right? And then you're just gonna choose the diagonal. Assume that these are the other hidden edges. And then you're gonna select one of these 4 diagonals of this cubic shape. So this is gonna give us the one hypotenuse and this edge and this edge. This edge height should be A. We agreed for this triangular shape that this edge will be A square root of 2, and this is gonna give us at the end that this hypotenuse will be the A square root of 3, right? A square root of 3, which you can, even if you consider the vector analysis, and we do have A, like A along X, A along Y, A along Z. So this is gonna give us, and to end up with the magnitude of this vector, this is gonna give us A square plus A square plus A square. This is gonna give us at the end A square root of 3. So there are lots of ways you can do the calculation for this diagonal from the vector analysis, or you can do it from the trigonometric analysis or the trigonometry of this shape, or the geometry analysis. Okay, anyway, we do have this A, and we agreed that over this main diagonal there should be, so if we draw this triangle one more time in this way, so over this one there should be 2 atoms, 1 atom at this corner, one atom at this corner, and there should be another atom in the middle. So this gives in total that this edge here is 2r here. This distance is just 1r, 1r. So we're going to end up that 4r equals a square root of 3, which going to give us a equals 4r over square root of 3, which this relation that we have proved before. Then the next step, the second step, is just to calculate the volume of atoms that form this unit cell. Atoms in the BCC unit cell. This volume, it should be Vs, which we agreed that we're going to give it a symbol as Vs stands for sphere or atoms or whatever. This is going to be 2 atoms because we agreed in BCC crystal structure. This should be BCC crystal structure. We do have only 2 atoms. 2 atoms times the 4 divided by 3 by r cube, which is going to be the volume of the sphere. So this is going to give us in total 8 divided by 3 by r cube. This is the volume of the atom. Then the third step is just to calculate the volume of the entire unit cell. This volume of the unit cell Vc, it should equal to a cube. Because why a cube? Because the volume of any cubic shape is just the cube of the side edge of or the length of the side of this cube, which is going to be a cube, and we already got a in terms of r up there, so this is going to be 4 divided by square root of 3 cube times r cube. I'm just calculating the cube of this term. So this is going to give us the volume of the sphere, which will be 64 divided by 3 square root of 3 r cube. This is going to give us the volume of the unit cell. Then the fourth step and the last step, your objective is just to calculate the atomic packing factor. The atomic packing factor, which should equal to the volume of the sphere or the atoms divided by the volume of the unit cell. This is going to give us the 8 divided by 3 by r cube divided by the 64 divided by 3 square root of 3, and we do have r cube. So this r cube will be cancelled with the r cube. The 3 definitely will be cancelled with the 3. The 8 will be eliminated with the 64 to give us 8 in the denominator. So this is going to give us 8 divided by square root of 3 in the denominator, and on the top we'll have pi. So this is going to give us, the pi on the top, and times square root of 3 divided by 8, right? This divided by 8. So this is the exact value of the atomic packing factor for BCC crystal structure. If we did the calculation, we're going to end up with 0.68017. If we round this number to considering only 2 decimals, so we're going to end up with 0.68 as the atomic packing factor that we already calculated for the consider for the BCC crystal structure. So this is simply for the BCC crystal structure. It is very common, but there are some different things. One of the things that there is no atoms at the centers of the faces, and instead we have one atom in the center of this cubic shape. And this will end up with some differences in terms of the number of atoms that located inside one unit cell. It is just 2 atoms instead of 4. The coordination number, it is 8 instead of 12, and the atomic packing factor, it is 0.68 instead of 0.74. Make sense? Now let us do the same for the third crystal structure, which is the HCP, which is hexagonal closed packing crystal structure. But the geometry, it is totally different than the other 2 previous types. Here in the hexagonal closed pack HCP crystal structure, it is hexagonal. This comes from the title or the name of this crystal structure. So the unit cell of an HCP crystal structure, it is hexagonal geometry. The other 2 types were cubic geometry. This is one different thing, with 3 layers of packed atoms. So that's why we got close packed HCP crystal structure, because we may have another hexagonal crystal structure, but the arrangement of atoms inside this hexagonal crystal structure could be different. So the hexagonal close packed crystal structure, it contains the geometry, it is hexagonal, it has a hexagonal shape. This is one thing. Another thing, it contains 3 layers of atoms who are packed together to form this geometry. Make sense? So how these three layers of atoms are arranged and how many atoms would be located inside one unit cell, what is the coordination number, all of these things will be calculated as we have done it for the FCC and Bcc crystal structure. So these layers are arranged in this way. On the top and bottom layers, we do have top layer, bottom layer. As already shown here in this representation, this is one unit cell of the HCP crystal structure. This is HCP crystal structure. This is HCP crystal structure. And so we do have one top layer, one bottom layer, one top layer, one bottom layer, top layer, bottom layer. And there should be middle layer. So the top and bottom layers of the unit cell consist of 6 plus 1 plus single atom. So in total, the top and the bottom contains 7 atoms. 6 atoms at the 6th corner. In a hexagonal shape, it has 6 corners, right? 1 corner, 2nd, 3rd, 4th, 5th, and 6th. So these are 6 corners, and there should be 1 atom at the center of this hexagonal face. So on the top layer or the top face, it has a hexagonal shape. There should be an atom at every corner. So this gives 6 atoms at the corners. And here I'm talking about the count, the locations of the atoms, not how many portions. I'm not discussing that this atom, it should be 1/6 of this entire atom. No, assume that it is a complete atom for now. So there should be 1 atom, because here I'm discussing the geometry. I'm not counting how many atoms. For the geometry discussion, we should have 1 atom located, its center located at the corner of this hexagonal face. So these are 6 on the top, and plus in addition to this, there should be 1 atom located at the center of this hexagonal face. This is for the top layer and the same for the bottom layer. Here we are not counting how many atoms. Forget about the number of atoms, just we are allocating the atoms, how these atoms are arranged. But how about the middle layer? The middle layer, it contains only 3 atoms that form a triangular shape. So the middle layer contains 3 atoms that form a 1 triangle. As already represented, in all of these are different ways of representing the same hexagonal crystal structure. So we do have 1 in the center and 1 at every corner of the top and bottom surface, and 3 that form a triangle, a specific triangle in the core, in the middle. As here, these are the 3 atoms that located in the center or the middle layer. These are the 3 atoms that located in the middle layer, and these are the atoms on the top and the lower surface of the hexagonal closed back crystal. Make sense? This is from the geometry. Also, another thing that related to the geometry, that it contains 1 unit cell of the HCP crystal structure contains 6 atoms. In the FCC, where only 4 atoms, BCC 2 atoms, here we have 6 atoms. Why it is 6 atoms and how these atoms are formed? 6 atoms were calculated at every corner of the top and lower surfaces. At every corner, there should be an atom. This atom is shared between 6 unit cells, not 8 like the cubic case. In the cubic crystal structures, the corner atom, it is shared among or between 8 atoms. Here it is shared only between, it can be shared between only 6 only. There is no any other option. It can be shared between 6, only 6 unit cells. The atom that located at the corner can be shared between 6 unit cells. It means that every single unit cell will take 1/8 of that atom. So 1/6 of that atom. So 1/6 times 6 atoms at this corner. This gives us 1 atom for the corners. If you repeat it for the other lower surface, you're gonna end up with another atom. So we do have 1/6 on the top times 6 atoms, 6 corners, and on the bottom surface we do have also 1/6 times 6 corners. This is one thing. In addition, over the top and lower surface, there is an atom that located at the center of that face. This atom, it will be shared by 2 unit cells, only 2. It means that every unit cell gonna take a half of it. So it is 1/2 of the atom will be for just 1 unit cell. So it is 1/2 on the top and there is another 1/2 on the bottom. So this is going to give us 1/2 of an atom on the top, 1/2 on the bottom surface. So in total, how many atoms that form the top surface? It will be 1.5 atoms. On the top, there should be 1.5 atoms. On the bottom surface will be the same, 1.5 atoms, because they are identical. So we're going to end up in total for the bottom and top surfaces 3 atoms. In addition, on the middle layer, we do have 3 other atoms. This gives us in total 6 atoms forming the unit cell for HCP crystal structure. So at the top and bottom layers, because they are identical, so that is fine to discuss them together at once. Layers of the unit cell, each corner atom is shared with 6 unit cells, and the central atom is shared between 2 unit cells. This gives 1/6 of each of the 6 corner atoms plus half of each of the face center atoms, which gives in total 3 whole atoms for the top and bottom layers. In addition to these 3 atoms, there are 3 other atoms that located at the middle layer of the unit cell. Therefore, we would have in total 6 whole atoms that form the unit cell of HCP crystal or unit cell as we discussed. Make sense? So it is 1/6 at the corners and 1/2 in the center of the top and lower surfaces. This gives 1/2 on the top, 1/2 on the bottom, in total 3, and 3 in the middle layer gives 6 atoms that form the HCP crystal structure. How about the atomic backing factor and the coordination number? Let us start with the coordination number. In order to understand or calculate or count how many atoms that could be enabled for any atoms that belong to this unit cell type of crystal structure, you should consider 2 adjacent unit cells, as we have done for the Fcc crystal structure. But in the BCC, we consider only 1 unit cell. And we choose the core atom and we counted the other neighbor. This is the simplest case. But for the Fcc, we had to choose and assume 2 unit cells side by side. Here we have to do the same for the HCP. For the HCP, if we assume that we do have 2 unit cells side by side, and we're going to choose this atom that located at the common surface between them as we have done for the Fcc. Like, assume that this is 1 unit cell on the top, hexagonal shape, and there is another unit cell on the bottom. There should be, if they already one on the top of the other one, there should be a common surface between them which is gonna have a hexagonal shape. This is the common surface that I'm talking about. And let us choose, as we agreed based on this geometry, this crystal structure, there should be an atom located at the center of that face. Let us count the neighbors of this atom. This is gonna give us 12, like the Fcc crystal structure. So there is very similar things with the Fcc crystal structure. So first of all, there should be 1 atom here, right? And there should be another atom here, another atom here, another atom here, another atom, another atom. This in total gives 6 atoms over the same face that is common with this atom or the common surface between the 2 unit cells. This gives in total 6 atoms. So this is 1 layer. Like this is atom, 2nd, 3rd, 4th, 5th, and 6th. So these are 6 atoms surrounding this atom that I choose. This is the atom in the middle that I'm choosing here, counting its neighbor. In addition, on the top, remember that this unit cell contains 3 layers. So I won't gonna move to all the other top layer. No, I'm just gonna consider the other 3 atoms. There should be 3 atoms in the core, 3 atoms here in the middle of this unit cell on the top, and there should be another 3 atoms that located in the middle layer of the other unit cell. These 3 atoms are neighbors to the same atom. These 3 atoms are neighbor to the same atoms, So we do have 3 on this middle layer of the top unit cell, and we do have 3 other atoms of the middle layer of the bottom or the other unit cell, and over the same common face we do have 6 atoms. So this gives in total 3 plus 3 plus 6. This gives us in total 12 plus. This gives us in total 12 atoms at the coordination number 12, which is going to be the same as the Fcc crystal structure. But being the coordination number identical to the one of the FCC crystal structure, this doesn't mean that these two structures are the same. No, they are different. Different in the arrangement, different in the geometry. This is hexagonal, this is cubic. Here we are arranging atom differently than this one. Make sense? But they are having the same common coordination number, that is fine, but still they're gonna be two different crystal structure which will give different material properties as well. Make sense? So this is how we can calculate the coordination number for the HCP crystal structure. Now let us move to the calculation for the atomic backing factor. The atomic backing factor for the HCP crystal structure, it is identical. It is the same value as the FCC crystal structure, of the same value, but definitely we're still talking about a different crystal structure. So the common between the FCC crystal structure and the HCP crystal structure is the number, coordination number, it is 12 in both, and the atomic backing factor is exactly the same as 0.74. It is just by chance for these two crystal structures, but they are still two different crystal structures. So how we can calculate the atomic backing factor? We're gonna stick to the same procedure. The first step, if you remember, your objective is just to calculate A, which is the side edge, in terms of R. But remember, here's something that is very important for the FCC, for the HCP crystal structure, that is different than the cubic crystal structures. In the FCC or BCC, the crystal structure or the unit cell has a cubic shape. And the cube as a geometry, forget about material science, as a geometry, it requires only one geometrical parameter, which is A, which is the side edge, that defines the geometry of a cube. In a cube, it can be represented by one dimension, like A, and this A will be repeated the same for all edges for this cubic shape. But how about any hexagonal shape? The hexagon or the hexagonal crystal structure, it requires two dimensions, two parameters, not just one. One is this side edge of the hexagonal face. Any hexagonal face, its edges, it should be identical. They are equal. Like it has 6 edges, 1, 2nd, 3rd, 4, 5, 6 edges. All of them, they do have the same size. They do have the same length. This A is repeated over the 6 faces or edges of the hexagonal face. The same thing for the top. So A, it is one of the geometrical parameters that needed to describe the edge length of the hexagonal faces of the HCP crystal structure or unit cell. But in addition to this one, there is another parameter which is C. This C, it is the height of the hexagon. This C, it is the height of this hexagonal shape. This is another parameter. We didn't have this one before in the cubic. In the cubic, this height, the height, it is equal to the side edge. Both are A. So A was the only geometrical parameter, but here we have C and A. The region between C and A, it is that C over A equals 0.633, which exactly it's gonna be that C equals the 2 square root of 2 over 3A. This is the exact relation. How C is going to be related to A, which is this side edge, based on the geometry that depend on the radius of the atoms. These atoms, there is a condition for them. The condition is that all of these atoms should be tangent to each other. They should be in contact to each other. So to achieve this requires that C, it should be in relation to A through this relation. If you change this relation, these atoms, they won't gonna be tangent. They won't gonna be touching each other, which is not a case for any material. All the material with hexagonal closed back, all atoms should be tangent together. It means that this C will be 2 square root, it should be 2 square root of 2 over 3 times A, which A is the side edge of the base or the top surface of the hexagonal faces. Make sense? So this is how C is going to be related to A. So the objective here to calculate the atomic backing factor, we should calculate not just A, we should calculate the C and A in terms of R. So these are two geometrical parameters that should be calculated in terms of R. What is R again? It is the radius of the atom itself. And you should keep in mind that C, you should remember and memorize this relation that C equals 2 square root of 2 over 3 times A. This is how C is going to be related to the side edge of the unit cell. Make sense? So, again, the objective is just to calculate A in terms of R. So let us calculate A in terms of R, then we can calculate C. So if we consider a hexagonal crystal or unit cell, should be in this way, right? And we said that this should be the base, and there should be some hidden, these are the other hidden edges. So we said that this edge, it should equal to A, right? So we need to calculate A in terms of R. Also, we agreed that there should be an atom that located at the corners. At every corner, there should be an atom. So this means over this corner, there should be an atom. Its center, the center of that atom, it will be that corner exactly. The same thing for the other corner. And another condition is that these two atoms should be tangent. All atoms should be tangent. It means that this distance from this point up to this point, let me, if I change the color just to make it clear. For example, the distance from this center to this point, this distance should be R, which is the radius of this atom, and the distance from this point to this point, it should be another R. So in total, we're gonna end up that A is gonna be equal to 2R. Agree? Based on the geometry. In the meanwhile, we do have, so this is A in terms of R. In the meanwhile, we do have C equals 2 square root 2 over 3A, which is gonna be just substitute for this relation times 2R. This is gonna give us in total 4 square root of 2 over 3R. So this is gonna give us the C in terms of R and the A in terms of R, and this is for the first step. Make sense? Now let us move to the second step. Step 2. The second step, as usual, is just to calculate the volume of atoms that form this unit cell, which is Vs. We said that this volume, it should equal to the 6. We do have 6 atoms that form the HCP crystal structure, right? So it means that the volume of these atoms should be 6 times the volume of the sphere, which is 4 over 3 by R cube. If we did the calculation, this is going to give us 24 over 3 by R cube, which definitely going to give us 8 by R cube. This is the volume of the 6 atoms that form the HCP crystal structure, as we mentioned. 3. Then you're just going to calculate the unit cell volume. The unit cell volume. This volume, it's going to be the Vc. Here it is hexagonal shape. It is not a cubic shape as the other types. So the volume for this hexagonal shape, and this is the thing that you have to memorize it as well, it is 3 square root of 3 divided by 2a square times c. This is the volume of any hexagonal shape. Here we are talking geometry, not material science. For any hexagonal shape, it is 3 square root of 3 over 2a square c. As we said, for example, the volume for the sphere, it is 4 over 3 by R cube, and the volume for the cube, it is a cube. So the volume for any hexagonal shape is going to be 3 square root of 3 over 2a square times c. But we already calculated, we have calculated this a and c in terms of R. So we're going to plug this data here to calculate the volume. So it's going to be 3 square root of 3 over 2 times a square, which is going to be 4r squared. Right, the square of a times the c, which we just calculated as 4 square root of 2 over 3r. Then if we do the calculation and the simplification of all of these things, we're going to end up with 24 square root of 2 times r cube. So this is the volume of the unit cell. This is the volume of the 6 atoms that form this unit cell. Then the atomic packing factor, and this is the fourth step. So the fourth step, calculate the atomic packing factor, which is going to be the volume of the sphere or the atoms divided by the volume of the unit cell, which is going to give us, if you divide this one by this one, this is going to give us at the end pi over 3 square root of 2. This value, this is the exact value of the atomic backing factor for the HCP crystal structure, which if we did the calculation, we're gonna end up with 74.048. If we round this number, we're gonna end up with 0.74, which is exactly the same as the Fcc crystal structure. Make sense? There is very important thing to notice here. The atomic backing factor for the HCP, it is 0.75. For Fcc, it is 0.75. The same number, yes. But it is not necessary to be this exact same one. Why? Because probably for some reason, you could have for the Fcc crystal structure a number, the exact number, it is not exactly the same as the atomic backing factor for the HCP. But if you round these two numbers up to the two first decimals, you're going to end up with the same number. But this is not necessary for any two crystal structure. But for the Fcc and HCP, they are exactly the same. Why? Because of this number. Here we got the atomic backing factor as pi divided by 3 square root of 2. If you compare this value to the previous value that we got it before for the Fcc, we got the same fraction, pi over 3 square root of 2. It means that the atomic backing factor for HCP and Fcc, they do have the same exact value. It is pi over 3 square root of 2. But for both of them. That's why the 0.75 indicate also that this atomic backing factor is the same for the Fcc and HCP crystal structure. So what is the common between these two crystal structure, HCP and Fcc? They do have the same coordination number as 12. They do have the same atomic backing factor, which is 75% of the crystal will be filled with atoms. This is for the atomic structure for these crystals as explained. Make sense? So this table here shows the different, like a summary of the different atomic radius or the different values of the atomic radius, which is R. This is the radius of the atom and this is R. So this is like two halves of the table. Like these are some material, these some other materials. Okay, and this is the crystal structure type, whatever it is, Fcc or HCP or Bcc. As I mentioned, why we are considering these three? Because this is the common. These three crystal structures are very common for many of the commonly used metals that use for engineering application. If we're going to talk about aluminum, it has Fcc crystal structure. The cadmium, it has HCP crystal structure. Chromium, it has Bcc crystal structure. Copper has Fcc crystal structure. We do have some like titanium and titanium. It has HCP and Bcc crystal structure. So for iron, it has Bcc crystal structure. We do have also another type of iron, by the way, that has Fcc crystal structure. So it means that you may have the same material type but with different crystal structures. These two material types of two different crystal structures, they do have different properties. As I mentioned, you may have an iron with Fcc. You do have another iron type with Bcc. These two ions still the same element as Fe in terms of chemistry, but in terms of atomic structure or crystal structure, they are different, and that's why they are different in properties. Also, we may have an aluminum material with Fcc crystal structure, another one with Bcc crystal structure. They are different. Okay, and so on. So this depends on it is not just the material type, it is not just the element type, it is not just the atom type, it is also the way of arranging these atoms. You're gonna end up with different properties. For example, for aluminum with Fcc, it is commonly known to have Fcc crystal structure. So its atomic radius has this value as 0.1431 in nanometer. As I mentioned, a nanometer equals 10 to the power negative 9 meter. This is how you convert from nanometer to meter to do the calculation. So these are the common, so all of these are different metals with different, like different crystal structures and their corresponding values of the atomic radius. Make sense? Alright, so the last thing that we are going to cover is the calculation of the theoretical density of a metallic crystal. If you have a metal crystal, and this is one of the things, how this atomic structure would influence the different properties, whatever mechanical properties, chemical properties, physical properties of the material. One of these physical properties of the density, so how it would be related to the atomic structure, or in other words, how it would be related to the atomic backing factor. We mentioned that this atomic backing factor, it gives indication how this unit cell is crowded or filled with atom. Is it crowded or not? It depends on the atomic backing factor. Like, for example, if for Fcc and HCP, it is 70% of the crystal structure is filled with atom. The other is just void. So this definitely, somehow it should be related to the density that we knew for all of these materials. So for example, how we can calculate this density theoretically based on the considerations of the crystal structure. And is it going to be the same value that if we measure, because how we can experiment, how we can run an experiment to determine the density of any material, simply the density is related to the mass, and the mass could be related to the volume through the density relation, right? So simply, we're gonna say that this density, because it should be in terms of gram, and we're gonna discuss this unit things, gram divided by centimeter cube. So it should be mass divided by a volume. So simply, if you have a piece of material, and you know its volume, you can do the calculation, you can measure the edge, a cube. You can bring a cube of this material and you measure the edge to calculate the volume. So we can do some simple calculation to find the volume. And then you're gonna just find the weight or the mass of this cube of that material. If you divide the mass divided by the volume, you're gonna end up with this density experimentally. This is how we measure or do calculation experimentally for a real material for the density. Can we do it theoretically from these crystal structure things? Yes, we can do the same. And you're gonna end up with almost the exact same value if you measure it, very close. It means that the theoretical calculation of the density, it is the same as the measured one. So let us do the calculation for the density, show you how we can do this calculation. This is gonna be through this relation. Like rho, which stands for the density. So this rho, this is the density value for the material that depend on the crystal structure, equals N. What is N? This is the number of atoms associated with each unit cell of this material. As we mentioned, the Fcc crystal structure contains 4 atoms. So N, if the material has an Fcc crystal structure, its N value, this lowercase n, stands for 4, will equal to 4. If this material is a Bcc crystal structure, this N will be 2 atoms. If it is HCP, it's gonna be 6 atoms, and so on. So this N stands for the number of atoms that are filling the unit cell of this material, depending on its crystal type, depending on its structure type, crystal structure type. So N stands for the number associated with each unit cell of this material. A stands for the atomic weight. And the atomic weight, as we knew, it is very common. We have discussed this in the chapter 2. This depends on the atomic type or the material type. So depending on the material type, there is a certain value for the atomic weight, which you can Google it for any material. If you Google, for example, the atomic weight for copper, for aluminum, for iron, for any material, you're gonna find it over Google. And it had been reported by so many textbook of physics and other textbooks. So this atomic weight, it is known for all materials that we are experiencing as engineers. So they already this value is already commonly known. Even you can find some of the periodic table that reporting this atomic weight of the sum of the material. Okay, so this atomic weight number, it is a material property. And atomic weight, it is a material property, and it comes in grams. It comes in this unit as grams over mole, as we discussed in chapter 2. And this VC, this is the volume of the unit cell that we just calculated. We have been calculated this VC, which is the unit cell volume that depend on the geometry, and we are not considering how many atoms or the atomic distribution inside the geometry. We do have either cubic for the Fcc or Bcc, or the HCP for the HCP unit cell. Make sense? The Avogadro's number, this is the number that is needed, as we discussed in chapter 2, to convert from grams to mole, and the number and relate to the number of atoms that would be located in 1 mole of the material. So this Avogadro's number is 6.023 times 10 to the power 23, and you have to remember this number, it is equal, it means that 1 mole of the material, it contains 6.023 times 10 to the power 23 atoms per mole. So this is going to give us the Avogadro's number, which should be, which is a constant for any material that is independent of the material. And then if we plug all of these data into this relation, you can calculate the density. So let us consider this example of the calculation of the theoretical density for copper. Copper has an atomic radius R, so the material type is copper. Even if we're going to go back here to this table, the copper, it has Fcc crystal structure and its R, atomic radius, equals 0.1278, which we can round this number into 0.128. So that's why it is given here that it has atomic radius by this value, which is the same value, but we're just rounding the number. So R, which is the atomic radius, it is 0.128 nanometer. Remember, it comes in nanometer. And the Fcc crystal structure, it has an Fcc crystal structure as already shown in the table. And an atomic weight, so the atomic weight, which is Na, the atomic weight, which is A, I think, or Na. Yeah, it is the atomic weight, it is A. This is the atomic weight. It is given by the 63.5 joule divided by mole. So these are the units that you have to stick with. If you have the atomic weight in as grams over mole, and this is how it comes, and so you plug this Avogadro's number, and you do have, this is just a number. And in the meanwhile, you calculated the volume of the unit cell in terms of centimeter cube, and you plugged. So your objective is just to calculate the volume of the unit cell, but in terms of centimeter cube. And the atomic weight in many of the cases will be given in gram over mole. Then you're going to plug this data into this relation. Definitely the density will be obtained in gram over centimeter cube. This is for how you already achieve consistency for these unit systems. Okay. So these are the given data. It is required to calculate the theoretical density and compare it with the measured density that we have in the literature. The measured density, the measured density in the literature, we already have it by 8.94 gram over centimeter cube. So your objective is just to calculate the theoretical one and compare to this value. Make sense? So how we can solve this problem? Simply, your objective is just to calculate the volume. So you can start, for example, by calculating Vc, which is the volume of the unit cell. What is the unit cell type for? This depends on the unit cell type. For the crystal, for the copper, it is Fcc crystal structure. So for the Fcc crystal structure, it should be A cube. This is the volume because it is cubic. But in the meanwhile, you should replace A in terms of R. According to the Fcc crystal structure, we do have the A equals 2 square root of 2R. You have to acknowledge and remember this number, this relation. For A in terms of R, as we have proved it before, this should be cubed. If you did the calculation, this is going to give us in total the 6 square root of 16 square root of 2 R cube. Then your objective is just to substitute for R. That already given to you here by 0.128 nanometer. But remember that we need to calculate this volume in terms of centimeter. So we have to convert from nanometer to centimeter. This needs to multiply times 10 to the power negative 7. To convert from nanometer to centimeter, you need to multiply times 10 to the power negative 7. But if you multiply 10 to the power negative 9, you are converting to meter. We need it to centimeters. So this is going to give us the volume equals. Your objective is going to be 16 square root of 2 times the radius, it is 0.128 times 10 to the power negative 7 to convert to centimeter cube. To centimeter, just this value, that's just to convert from nanometer to centimeter. But if you replace the 7 with 9, you're already converting to meter. We don't need it in meter, we need it in centimeter. If you did the calculations, this is going to give us at the end 4.745 times 10 to the power negative 23 centimeter cube. So we got the volume in centimeter cube, and this is very important to achieve consistency in the units. Then your objective in the second step is just to calculate the density. It is just 2 steps. So second step, calculate rho, which is the theoretical density. Plug into this relation that we mentioned once before. It is N times A divided by the volume of the unit cell times the Avogadro's number, which is already given by 6, 0 in this value. So how many atoms that would be located in an FCC crystal structure? We mentioned before it is just 4 atoms times the atomic weight. For the copper, it is 63.5 divided by, and there is no need for conversion for units for this atomic weight, and the volume we just calculated by 4.74 5 times 10 to the power negative 23, and we are in a good shape. We're just gonna plug this value because it is already calculated in terms of the centimeter cube. Then times the 6.023 times 10 to the power 23. This is the Avogadro's number. You have to remember this number and use it. This definitely will be cancelled with the 10 negative 23. Then if you did the calculation, we're going to end up with the density as 8.887 grams over centimeter cube. If you try to compare this value to the measured value, we're already getting like almost the same number, right? It is 8 point, if we round to this 2 decimal, this is gonna be like 89 instead of 94. So this is gonna be 8.89 grams over centimeter cube, which is very, very close agreement with the foregoing results in the literature about this measured value. So this is the theoretical value that we got, and this is the measured value, which is very close. It means that the theoretical calculation for the density of this crystal structure or this material type, it makes sense. It can replace and substitute the experimental measurement as well. Make sense? So this is the objective of this video. It's just to discuss these 3 different, in detail, these 3 different crystal structure. Why these 3? Because they are common. Many of the metals, they do have this, one of these crystal structure. They are very common, but this doesn't mean that these are the only crystal structure. We do have so many other materials with different crystal structures, but these are the common things. Okay, so we have discussed these crystal structure. We distinguish between them in 3 things: in the geometry, in the coordination number, and the atomic backing factor. And we knew how we can calculate these 3 quantities for every one of the 3. Then we knew how the density would be related to the atomic backing factor, or the way of arranging atoms or the crystal structure through this relation. This is what we have covered over this part of the chapter 3. The next meeting we're gonna continue. We still didn't finish chapter 3. We're gonna continue working on chapter 3, but we are going to discuss more other physical quantities and relations that would be related for the crystal, for these 3 different crystal structure, like how we can identify the direction, the crystallographic direction, the crystallographic planes, the crystallographic points. So these coordinates or points, these quantities will be discussed in detail over the next videos for the chapter 3. Again, the importance of this chapter is just to fix some of the keywords and physical phenomena that we're gonna use for the next chapters. In addition, is to know how the material properties would be related to the arrangement of atoms inside the material structure. Right? So that's it for today or this video, and see you in the next lecture. Thank you so much, and see you.